Hello, and welcome back to Sensors and Sensor Systems. In this mini lecture, we'll focus on capacitive touch sensors and their use in both touch buttons and touch screens. Capacitive touch sensors, as their name suggests, works by generating a change in capacitance when a touch has occurred, either by a finger, a stylus, or another appropriate device. The touch can change capacitance in two major ways. First, by changing the dielectric constant between the plates of the capacitor, and second, by interfering with the electric field lines that couple the two plates or electrodes of the capacitor together. This is often done by providing a leakage path to ground or to somewhere else that steals voltage or current from the plates and therefore decreases the capacitance. Now let's take a look at how this works. First, we'll look at capacitive touch sensors that create a change in dielectric constant in response to a touch. And what we see here is someone's fingertip touching a touch sensor which consists of a ground plane shown in blue here and a sensor pad that together make up the two electrodes of the capacitor. And the two are separated in the absence of a touch by air, shown here in the semicircle. Now when the finger comes in contact with the overlay, the finger creates a change in dielectric constant in the capacitor formed between the sensor pad and the ground plane. And that change in capacitance is what dictates determining a touch versus the absence of a touch. The overlay itself is transparent, and it's usually provided to protect the underlying circuitry and sensor from damage and dirt and contamination, but it can also sometimes play a role in providing a high dielectric constant that works in concert with a touch to increase the sensed change in capacitance even more than if we were just looking at the presence of the finger on the ground and sensor pad combination itself. So the finger here does not actually lie between the two electrodes, between ground and sensor pad. But the fact that a finger has such a high dielectric constant compared to air means that the fringing fields, those that fringe outside of the capacitor, like this, are still affected by the presence of the finger, thereby changing the capacitance between these two electrodes, the sensor pad and the ground, via the dielectric constant. The difference in dielectric constant between air and human skin is so large that this actually works. By putting a dielectric constant of between 30 and 50, even on top of the overlay that separates the finger and the underlying sensor, provides a sufficient change in dielectric constant that we can sense a change in capacitance well enough that determines a touch. Now, what's important to remember about dielectric constants as well as resistance of the skin and the body is that they change according to frequency of interrogation. So if we run this system at the megahertz scale, we actually get a pretty large dielectric constant for skin, around 46. And that starts to drop if we run the whole system at much faster frequencies. So we'll assume here that we're looking at a low frequency interrogation around megahertz or lower that provide us the opportunity to capture a high dielectric constant in the sensor structure here, and that causes sufficient change in capacitance for us to be able to measure it as a touch. Now the second method is not much different from the first. In fact, we see here that we have the exact same structure. So what's different? Well, the human body is not just a capacitor, and the finger doesn't act just as a capacitor. So the skin on the finger also has some conductive properties, and those conductive properties through the skin can actually leak current or leak electric field away from the voltage that's applied from sensor pad to ground. And when it does that, it also has the effect of increasing the overall capacitance. So both these effects, the conductive effect and the insulating or dielectric effect, serve to increase the capacitance and therefore indicate a touch. Now, to get a handle on this, let's just take a look at a real simple circuit here, one that is extracting a single touch button, like a doorbell, for example. In this simple circuit, when we press the touch button, the doorbell, what we're doing is we're attaching a capacitor created by our bodies to ground that runs in parallel to the capacitance associated with the touch sensor itself. And when we combine those two capacitors, C body plus C touch, because they're in parallel, we can just add them, and we get a capacitance, a total capacitance, that's bigger than C at baseline. So the capacitance here increases as we expected and as we saw in previous slides. And then we just go ahead and put this capacitor into an oscillator whose frequency will change with the changing capacitance. And typically an increase in capacitance or a touch will result in a slower output or a lower frequency that indicates that presence of a touch. Now we can take all this and put it into an array level, so we eventually get to capacitive touch sensors or arrays that are appropriate for consumer electronics like smartphone touchscreens. When capacitive touch sensors are aggregated into arrays, they make a touchscreen, and we get an n by n resolution touchscreen defining how small an increment we can touch on the screen and still be detected as a distinct touch. In this example here, the rows are indicated by the Y electrode and the columns are indicated by the X electrode. And there are a number of different ways we can extract capacitance in the array or touchscreen fashion or configuration, and we'll look at two of those primary ways in the next slides. The first is the easiest to understand, the self-capacitance, where essentially it works like a touch button. We have a sensor pad in the underlying substrate, which has a protective layer over it to protect it from dirt, contamination, and mechanical damage. And the presence of someone's finger, or a stylus, or something else of appropriate dielectric constant creates a capacitance from the point of touch to ground. That, at some level, adds to the capacitance of the sensor itself, which is usually also referenced to ground, whether virtual or actual ground. And what that means is by tying the second electrode in our sensor to ground, we have what's called self-capacitance, where the capacitance of the self, or the finger, adds to the capacitance of the sensor and thereby creates an increase in capacitance that we use to determine touch. Like the previous example with the touch button, we can then run that capacitance through a 555 timer or an oscillator circuit, so we get a square wave or other periodically varying signal whose frequency determines whether there's been a touch or not. But there's a big problem with self-capacitance arrays or screens, particularly for modern-day electronics. So while self-capacitance touch button screens are very high resolution and the pixels themselves are small and easy to manufacture, the issue that we come up against is with multiple touches. But let's first take a look at how the whole array operates when we use the self-capacitance approach. What we do here is we measure the capacitance across each row, the total capacitance, and down each column. And when we tabulate those, when we see something that is above the baseline, we can determine that there's been a touch in that column and in that row. So for example, here we have a capacitance, a touch occurring at row 7 and along column 5. And what we see is that at row 7, we see an increase in capacitance, and we also see one in column 5. And that tells us basically that there's been a touch at the intersection of row 7 and column 5, as is shown right here. And the same thing happens along touch 2, which is in column number 2 and row number 3. We see the same effect there. Row 3 and column 2 both indicate an increase in capacitance. Therefore, we assume a touch has occurred at the intersection of that row and column. But here's the problem with doing things this way. It's very easy to confuse the real touch here with another possible pair of touches here. So what we can do is we could confuse, there's some ambiguity here. The real touch occurs here, but it's possible we could interpret the touch as this pair. So we don't know. Which pair of touches is it? Is it the one that we actually know is happening, or is it this ghost touch that could also come from interpreting our row and column capacitances? This creates an ambiguity with multiple touches that gets much worse as we have more than 2 touches, and it makes this self-capacitance approach inappropriate for any application where we'd be using multiple touches. To solve that problem, we use something called mutual capacitance, and although it's larger and requires more circuitry, it eliminates this problem that we have with ghost points or ambiguity in determining where an actual touch has occurred. And in mutual capacitance, instead of just having the one electrode referenced to ground, we now have 2 electrodes, neither of which are connected directly to ground. One creates a drive signal, and the other side, or the other electrode, receives that signal, and the magnitude or frequency of that signal will determine whether there's the presence of a finger or another increase in dielectric constant nearby the 2 electrodes. So what this gives us is the ability not just to control an entire row of electrodes or determine the capacitance of an entire column, but it allows us to determine capacitance change at single pixels. And with that, we're able to determine, without ambiguity, where multiple touches occur, and to do it for as many touches as someone can manage on their touch screens. So in the mutual capacitance scenario, we've seen that we can use these 2 electrodes now, consume more space and have more circuitry, but we can get rid of the ghost point problem and be able to detect an unlimited number of touches made at any given point in time. So in this example, again, we saw this with the self-capacitance, and we see here, since we're individually querying each pixel, each touch sensor in the array, there's no ambiguity. So mutual capacitance touchscreens eliminate ambiguity in multi-touch situations. However, they are also more sensitive to dust and dirt because the difference between touch and no touch, or delta C, is much smaller than for self-capacitance touchscreens. The baseline capacitance now will be that of a single pixel or a single touch in the array, and therefore is much smaller, and we're trying to determine a change in capacitance that's even smaller than that. So that makes things tricky, and it requires more complicated controller electronics to make sure that we can both extract that small capacitance and deal with the fact that one end of the capacitor is no longer grounded. So in general, we know capacitive touchscreens have a lot of advantages over resistive-based screens. First, they provide excellent multi-touch zoom, swipe, and pinch sensing with few errors and no ghost points through mutual capacitance, which we just discussed. They are highly sensitive and responsive to human touch or anything else that has a significantly different dielectric constant than air. They enable sharp, high contrast displays due to the thin, transparent top layer available for this approach, and they are not significantly impacted by cracks and scratches. They also don't deliver dead zones or areas where we can't detect a touch at all due to aging and degradation of the array. but they're not perfect. Mutual capacitance screens could have low resolution because of the space consumed by the circuits at each touch sensor or pixel. Self-capacitance screens can be totally unresponsive to gloves, stylus, or other objects whose dielectric constant isn't significantly different than air. And both types of touch screens are vulnerable to inadvertent touches, the whole pocket dialing problem, and both types of touch screens can perform poorly when they're dirty. So this has been just a brief introduction to how capacitive touch sensors and touch screens work. There are multiple ways to construct these screens, and they're different depending on the needs of the application. But basically, a touch increases the capacitance of a self-capacitive touch sensor, but decreases the capacitance of a mutual capacitive touch sensor. Regardless of whether capacitance goes up or down with a touch, both types of sensors are very sensitive to dust, dirt, and moisture. So that completes a brief overview of capacitive touch sensors. Thanks for joining us today, and we hope you'll join us again soon.